All right, welcome back to our Quantum Fortnight series. Last time, we kind of dipped our toes into the quantum realm. Well, today, we are taking a running leap and diving headfirst into the deep end. We're talking about the stuff that made Albert Einstein himself scratch his head and call it spooky action at a distance. So yeah, get ready, because things are about to get really, really weird.
So I want to kick things off with this question. Just let it hang in the air for a second. What if everything you think is solid and real and definite isn't? What if it's all just a shimmering cloud of possibilities, a fog of maybes that only snaps into focus when something or someone forces it to? And hey, this isn't some late-night philosophy session. This is the actual world we're about to explore.
So think of this as your own private after-hours tour of the quantum zoo. And let me tell you, the exhibits in here, they defy all logic and common sense. We're going to come face to face with the 6 strangest, most mind-bending phenomena in the entire universe. These are the rules that build everything around you, but they operate in ways that honestly feel like straight-up magic.
Okay, so here's our itinerary. First, we'll see how one little particle can literally be everywhere at once. Then we'll figure out how just looking at something can change its fate forever. After that, we'll witness that spooky connection, watch particles ghost right through solid walls, discover why we can never truly know everything, and for the grand finale, we'll see what happens when reality just breaks.
Right, let's get into it. Our first stop on the tour is the absolute bedrock of all quantum weirdness, superposition. This is the wild idea that particles don't just exist in one state. Instead, they live in this kind of ghostly haze of all their possible futures, all happening at the exact same time. So instead of an electron being in one specific spot, it's described by what's called a wave function. You can think of this like a recipe that contains every single possible outcome. The electron is in a very real way, here and there. It's spinning clockwise and counterclockwise, all at once. It's a cloud of pure potential. And the classic proof of this is the double-slit experiment. It's a total mind-bender. You fire electrons, one by one, at a wall with 2 slits in it. You'd expect to see 2 lines on the screen behind it, right? Nope. What you get is a complex interference pattern, like ripples in a pond. And that pattern could only happen if each individual electron went through both slits at the same time and then interfered with itself. It's not that we don't know which path it took, it's that it fundamentally took all of them. So, if you remember one thing from this exhibit, make it this. At its core, reality is just a cloud of possibilities. Particles are out there exploring every single option they have until something comes along and forces them to pick one. And that idea of forcing them, well, that brings us neatly to our next stop. All right, next stop on our tour. What does it actually mean to force reality to pick a card, any card from that deck of possibilities? This, my friends, is what physicists call the measurement problem, and it is a doozy. See, measurement in the quantum world isn't just passively looking at something. It's not like checking the color of a car. You looking at it doesn't change the paint job. Down at this scale, to observe means you have to interact. You have to poke it with a photon or hit it with a magnetic field, and that very act of poking forces that whole cloud of possibilities to just collapse. It instantly picks one random outcome and poof, that's the reality we get to see. Now, this leads to a seriously trippy thought experiment. Imagine your friend is in a sealed lab. They measure a particle and see it become spin up. For them, reality is fixed. But for you, standing outside, you have no idea what they saw. So from your perspective, the entire lab, your friend, their equipment, the particle, is now in one giant superposition. It's a state of both friend saw spin up and friend saw spin down at the same time. Yeah. Reality itself can be relative. Its fate is decided for your friend, but it's still just a possibility for you, right up until you open the door and ask, hey, what'd you get? So here's another key idea to hang on to. Think of a quantum state like a bowl of wobbly, unset jelly. It's got the potential to be solid, but it's still fluid and shimmering. A measurement is like poking that jelly with a spoon. The whole thing instantly sets into one fixed shape.
Observation isn't just looking, it's the nudge that makes reality snap into place. Okay, things were already pretty weird, but you might want to brace yourself because we've arrived at the spookiest exhibit in the entire zoo. What happens when you link two particles together in that fluid, wobbly state? You get quantum entanglement, the thing that bothered Einstein so much. Okay, imagine you create a pair of entangled particles. Let's call them A and B. They're linked in a special way, like two sides of the same coin. If one is heads, the other has to be tails. Now you separate them. You send particle B 1,000 kilometers away or to the moon, it doesn't matter. The very instant you measure particle A and see that it's spin up, heads, you know with absolute certainty and zero delay that particle B is now spin down, tails. It's not that a signal shot between them. It's that they were never really two separate things to begin with. And let's be really, really clear here. This is not communication. Nothing is traveling faster than light. The mind-blowing takeaway is that these two particles share a single existence that stretches across any distance. They have one unified wave function. So when you poke one part of it, the whole thing responds instantly. It just completely demolishes our everyday idea of things being in separate places. From spooky connections to just plain impossible actions. Our next exhibit shows how quantum particles can do something that looks for all the world like pure magic. They can just walk right through solid walls. This is called quantum tunneling. So how on earth does that work? Well, remember, a particle isn't a tiny little marble, it's a wave of probability. And that wave doesn't just slam into a wall and stop. A tiny, tiny little piece of that probability wave can actually leak through the barrier. That means there's a small but very real, non-zero chance that the particle will just blink out of existence on one side of the wall and pop up on the other, without ever having the energy to actually climb over it. And this isn't just some wacky theory. The fusion happening in our sun right now depends on tunneling. The memory in your phone relies on it. It's real and it's happening everywhere. So here's the key. This isn't about breaking the laws of energy conservation. It's about following the much stranger laws of probability. For a probability wave, a solid wall isn't an absolute do not enter sign. It's more like a place where the probability of being there is incredibly low, but never zero. Okay, next up on the tour is a bit of a downer for all you perfectionists out there. It turns out there are some things you just can't know. Nature has a built-in fuzziness, a fundamental uncertainty that we can never, ever get rid of, no matter how clever we are or how good our instruments get. This is Heisenberg's famous uncertainty principle. It basically says there are pairs of properties that are linked in a cosmic trade-off. The classic example is position and momentum. That's where a particle is and where it's going. The more precisely you nail down its exact position, the fuzzier and more uncertain its momentum becomes, and vice versa. If you measure its momentum perfectly, its location becomes a complete blur. It's like a cosmic seesaw. When you push one side down with certainty, the other side flies up into uncertainty. And I've really got to hammer this point home. This has nothing to do with our equipment being clumsy. This isn't a technological limit we can fix with a better microscope. This is a fundamental, non-negotiable, baked into the fabric of the universe feature. Reality, at its most basic level, is just inherently fuzzy. Okay, for the grand finale of our tour, let's take all these bonkers rules we've just learned, superposition, measurement, entanglement, all of it, and let's smush them all together. What you get are situations that don't just bend our intuition, they snap it clean in half. Welcome, ladies and gentlemen, to the quantum paradoxes. Ah yes, the most famous cat in all of science. The setup is this. You put a cat in a sealed box with a tiny radioactive atom. If the atom decays, it releases a poison and, well, you know. The atom is a quantum object, so until you look at it, it's in a superposition of both decayed and not decayed. But since the cat's fate is tied to the atom, that means the cat itself is in a superposition of being both alive and dead at the same time. Our brains scream, that's ridiculous, but quantum logic just shrugs and says, yep, that's how it works. And that's our last big takeaway from the tour.
These paradoxes, they're not mistakes or flaws in the theory. They're actually road signs. They're pointing directly at the places where our everyday, common sense intuition completely fails us. They force us to let go of what we think reality should be and just accept what it is.
Whew, okay, that was a lot. Let's do a quick lightning round recap of our tour. We've got particles existing in all states at once. We've got observation forcing one of those states to become real. We've got entangled particles sharing a single fate across the cosmos. Particles ghosting through walls, a fundamental ban on perfect knowledge, and logic that just breaks our brains. These are the strange, wild, but totally consistent rules of our universe.
So where does that leave us? Well, it leaves us with a really profound thought. Maybe, just maybe, we've been asking the wrong question this whole time. The quantum world seems to be telling us that reality isn't some static thing that's just out there. It's a dynamic, interactive process. The question isn't what is real, the real question is, when and how does it become real? We've just gone on a wild tour through the fundamental strangeness of reality. But, this isn't just some philosophical head-scratcher. The big question is, so what? What happens when we stop just marveling at the weirdness and actually try to use it? Well, the answer is, you get the future. That's right. In the final part of our series, we're going to see how scientists are basically becoming wizards, taking these bizarre rules and using them to build world-changing technology. We're talking about quantum computers that can solve problems we thought were impossible, unhackable communication that's guaranteed by the laws of physics themselves. We'll even ask if human teleportation is on the table. This is the next great technological revolution, and it's built on all this weirdness.
So, today was all about revealing the fundamental strangeness of how reality works. Next time, we're going to show you how we can put that strangeness to work for us. You are not going to want to miss the final part of our Quantum Fortnight, where we see how science fiction is literally becoming science fact. I'll see you there.